Defect inspection in semiconductor industry. Defect inspection plays a critical role in ensuring the quality and reliability of semiconductor devices throughout chip manufacturing. As device features shrink and complexity increases, detecting and analyzing even the smallest defects becomes essential. The process begins with detection, using advanced inspection tools to identify anomalies on wafers, including particles, pattern defects, and surface contamination. These tools include optical, E-beam, and other high-resolution techniques capable of spotting nanoscale issues. Next is analysis, which focuses on identifying the root causes of defects. By classifying and tracing them back to specific process steps, manufacturers can uncover patterns or systemic issues. This analysis is crucial for driving continuous improvement. Finally, prevention involves using insights from detection and analysis to implement corrective actions. This helps improve process stability, reduce scrap rates, and increase yield, making defect inspection a cornerstone of semiconductor manufacturing excellence. What are semiconductors? Semiconductors are materials that can control electrical current, acting either as conductors or insulators depending on the conditions. This unique behavior sets them apart from traditional conductors like copper and gold, which always allow current to flow, and from insulators like rubber and glass, which block electricity entirely. Silicon and germanium are common examples of semiconductors due to their ability to toggle between conducting and insulating states. What makes semiconductors so special? First, they're switchable, meaning they can be turned on and off electronically, enabling the core function of digital logic. Second, they are controllable. Engineers can precisely regulate how much current flows through them. Finally, they're miniaturizable. Semiconductors can be made incredibly small, allowing billions of transistors to fit on a single chip. These properties make semiconductors the fundamental building blocks of all modern electronic devices. What are semiconductors? Found everywhere. Semiconductors are truly everywhere in our modern world. You can find them powering the processors and memory inside smartphones, enabling high-speed performance and multitasking. In computers, semiconductors are central to CPUs and graphics cards, allowing us to compute, render images, and access vast amounts of data. Cars now rely heavily on semiconductors for engine control, advanced driver assistance, and infotainment systems. In the entertainment space, TVs use semiconductors to manage both display functions and audio systems. In the medical field, devices and sensors utilize semiconductors to monitor, diagnose, and treat patients with precision and reliability. Even the internet depends on semiconductors for all types of network equipment, from routers to data centers. And here's an amazing fact. Silicon is the most commonly used semiconductor material, and it comes from sand. That's right, ordinary sand is purified and transformed into the high-performance chips that drive global innovation. Why defect inspection matters? Defect inspection is essential in semiconductor manufacturing because the financial, technical, and safety stakes are extremely high. From a financial standpoint, even a single defective batch of chips can cost over $100 million. A seemingly small 1% defect rate leads to a 10% yield loss. Given that advanced chips cost more than $10,000 per wafer, even minor issues can result in substantial losses. On top of that, product recalls can cost millions more in damages, legal liability, and customer trust. Quality assurance is equally critical. Industries that depend on semiconductors, such as automotive, medical, aerospace, and data centers, demand ultra-high reliability. The goal is 99.9% uptime or better. Any defect in safety-critical systems could have life-threatening consequences. To meet these high expectations, manufacturers aim for defect rates measured in parts per billion, ppb. This level of precision requires adherence to strict industry standards, including ISO 9001, IATF 16949 for automotive, AS 9100 for aerospace, and IEC 62304 for medical devices. These standards drive global consistency and compliance. Why defect inspection matters? Prevention is success. The timing of defect detection has a huge impact on cost and product quality. When a defect is caught through early detection, the cost might be just $1. But if the same defect is only found after post-production, that cost can increase tenfold to around $10. And if it's not detected until a field failure, the cost skyrockets to over $100, not including the potential damage to customer trust or brand value. Early detection saves money, prevents scrap, and avoids large-scale recalls. Defects also impact performance. They can reduce speed by limiting processing power, lower efficiency through higher power consumption, shorten longevity by reducing the device's lifespan, and harm stability, especially under varying temperatures. Each of these factors can degrade user experience. Finally, consumer trust is at stake. A company's brand reputation depends on delivering quality. This builds customer loyalty, and loyalty drives market share. Strong defect inspection ensures all three. Early detection equals prevention success. Conclusion and future outlook. Defect inspection is not just a quality tool. It's a driver of progress in the semiconductor industry. As we look ahead, the future is now. Inspection technology is the cornerstone of semiconductor excellence, enabling the reliable performance of everything from consumer electronics to critical infrastructure. To meet the growing complexity of devices, the industry must continue to invest in advanced inspection technologies. This includes tools with higher resolution, faster throughput, and greater sensitivity. Beyond hardware, we must innovate using AI-powered solutions. Artificial intelligence is transforming inspection by automating classification, predicting failures, and enhancing root cause analysis with speed and accuracy. And as complexity increases, it's vital to integrate multimodal inspection systems, combining optical, electron, and metrology techniques for a comprehensive view. As the quote reminds us, quality is not an act, it is a habit. Excellence in semiconductor inspection is more than best practice. It's a necessity that shapes the future of technology. Types of defects. Defects in semiconductor manufacturing are broadly categorized into physical defects, process defects, and contamination. Physical defects include crystal defects, like missing atoms, known as vacancies, extra atoms positioned where they shouldn't be, called interstitials, and disruptions in the orderly crystal lattice. Surface defects arise as scratches, pits, rough surfaces, or step edges that can interfere with layer uniformity. Structural damage involves serious mechanical issues like cracks, wafer breakage, and deformation stress, which can lead to device failure. Process defects focus on manufacturing precision. Patterning defects stem from misalignment, variation in line widths, or incomplete etching, all of which affect circuit fidelity. Deposition issues include uneven film thickness, poor adhesion, and unwanted variation in material composition. Doping problems may involve incorrect dopant concentrations, uneven distribution, or using the wrong dopant type. Contamination types include particles, chemical, and environmental sources. Particulate contamination involves dust, debris, or residues from tools or processes. Chemical contamination includes trace metals, organic residues, and ionic impurities. Environmental issues include moisture absorption, oxidation, and damage from static electricity, all of which can compromise device reliability. Defect severity, impact, and size matters. Defects in semiconductor devices are not all equally harmful. Their impact depends on severity. Critical, or killer, defects are the most serious, leading to instant device failure. These can render a chip non-functional, even before it leaves the fab. Major, or latent, defects don't cause immediate failure, but degrade performance over time, potentially leading to early product breakdown. Minor defects cause performance reduction, but may still allow the device to function within acceptable limits. Finally, cosmetic defects are purely visual and do not impact the device's electrical performance, but might affect packaging or customer perception. When it comes to defects, size is a major concern. The typical minimum detectable defect size is 50 nanometers. To understand how small this is, consider that a human hair is about 80,000 nanometers wide, a red blood cell is roughly 7,000 nanometers, and even a virus measures around 100 nanometers. Critical defects can be as small as 50 nanometers, making them 1,600 times smaller than a single strand of hair. Identifying such minuscule flaws requires highly sensitive inspection tools, underscoring the precision needed in semiconductor manufacturing. Defect causes. Understanding what causes defects in semiconductor manufacturing is key to preventing them. Equipment issues are a major contributor, responsible for around 65% of all defects. Tool wear is one factor. Components degrade over time, calibration drifts from optimal settings, and parts may become contaminated. Poor maintenance can worsen these issues, especially if cleaning is inadequate or the equipment is aging. Alignment problems, such as misalignment, focus issues, or registration errors, can compromise pattern fidelity on wafers. Tool matching is another challenge. Variations between tools, different suppliers, or tool version discrepancies can introduce inconsistencies across production lots. Material quality is the second major category. Substrates may have inherent crystal defects, surface roughness, or high impurity levels that degrade performance. Chemicals used in processes can vary in purity, degrade in storage, or become contaminated, each posing a risk to yield. Gases, if impure, high in moisture, or subject to leaks in the delivery system, can also introduce defects. Lastly, supply chain issues like vendor differences, inconsistent batches, or mishandling during transport can lead to process variability. Managing both equipment reliability and material integrity is essential to maintaining high yields and minimizing defects in semiconductor fabrication. Environmental and human causes of defects. Environmental conditions can significantly affect semiconductor manufacturing quality. Temperature fluctuations, whether from cooling system issues or uneven thermal gradients, can cause stress and distortions in wafer materials. Similarly, humidity must be carefully controlled, as condensation or overly dry conditions can impact both process chemistry and material stability. Vibration, whether from equipment or building movements, creates instability that can lead to misalignment and particle release. Cleanroom conditions are especially critical. Any disruptions in airflow, filter degradation, or failure to maintain cleanliness can introduce contamination at the microscopic level, jeopardizing yields. Human factors are equally important. Inadequate training, skill gaps, or errors by new operators can all lead to costly mistakes. Errors may arise from incorrect equipment setup, wrong process parameters, or unnoticed deviations during operations. Procedural issues, like outdated documentation, unclear instructions, or poor communication, can compound problems across shifts. Finally, operator fatigue plays a key role. Shift work, mental fatigue, and stress can impair judgment and reduce focus, making errors more likely. Maintaining environmental stability and supporting workforce training, procedures, and well-being are essential in minimizing human-induced defects in semiconductor manufacturing. Process variation impact. Process variations are a major contributor to defects in semiconductor manufacturing. One key cause is recipe drift, where process parameters gradually shift over time. These slow changes can go unnoticed, but accumulate until performance is compromised. Recipe drift alone accounts for 20% of all defects, making it the most common process variation issue. Tool variation is another critical factor. Even tools of the same model can behave differently due to wear, calibration, or subtle manufacturing differences, contributing to 15% of defects. Batch variation adds another layer of complexity. Differences between production lots, whether from raw materials or process inconsistencies, lead to 12% of defects. Finally, cross-contamination, which accounts for 8%, involves unintended transfer of materials or particles from one process to another. This often happens when equipment or transport systems are not adequately cleaned between steps. Together, these sources of variation can significantly reduce yield and reliability. This is why root cause analysis is vital. By understanding exactly where and how these variations occur, manufacturers can implement targeted corrective actions, prevent recurrence, and maintain high-performance standards across the fab. Defect causes. Semiconductor manufacturing defects originate from two major sources: equipment issues and material quality. Equipment-related problems account for about 65% of all defects. Within this category, tool wear is a leading cause, driven by component degradation, calibration drift, and part contamination. Maintenance issues, such as inadequate cleaning, aging machinery, and poor upkeep, also play a major role. Alignment errors can emerge due to misalignment, focus problems, or registration inaccuracies. Additionally, tool matching inconsistencies, caused by tool-to-tool variation, using different suppliers, or version differences, can lead to non-uniform results across production. On the material side, substrate quality is critical. Crystal defects, surface roughness, and impurity levels can introduce variability. Chemical issues stem from purity changes, degraded storage conditions, or contaminated supplies. Gases used in processes may carry moisture or be impure, or delivery system leaks may occur. Lastly, supply chain factors such as vendor variability, batch inconsistency, and handling damage introduce further risk. Together, these causes highlight where control and monitoring must be most rigorous. Environmental and human factors. Two additional major contributors to semiconductor defects are environmental influences and human factors. Environmental issues can subtly but significantly impact process stability. Temperature-related problems such as thermal fluctuations, gradient inconsistencies, and cooling system malfunctions can introduce variability across wafers. Humidity also plays a critical role. Poor moisture control, condensation, or overly dry conditions can interfere with sensitive materials and processes. Vibration is another challenge, often caused by building movement or equipment instability, leading to misalignment or measurement inaccuracies. Even within cleanrooms, particles, airflow disturbances, and improperly maintained filters can lead to serious yield loss if not tightly controlled. Human factors also contribute meaningfully to defect generation. Inadequate training can result in skill gaps and errors from inexperienced operators. Procedure issues, like poor documentation or outdated steps, introduce uncertainty and mistakes. Errors in setup, incorrect parameter inputs, or deviations from standard processes also add risk. Lastly, fatigue from shift work, attention lapses, or stress can reduce focus and accuracy, leading to preventable errors. Addressing these human and environmental dimensions is key to achieving high manufacturing quality. Process variation impact. Variability in manufacturing processes is a major contributor to semiconductor defects. One major source is recipe drift, where process parameters, such as temperature, pressure, or timing, gradually change over time. These slow shifts can result in deviations from optimal conditions, accounting for about 20% of defects. Another factor is tool variation. Even when equipment appears identical, small differences in calibration, wear, or setup can cause inconsistent results. Tool variation is responsible for approximately 15% of defects. Batch variation refers to inconsistencies between production lots. Whether due to subtle changes in materials, environmental shifts, or operator methods, batch-to-batch variability accounts for 12% of defects. Lastly, cross-contamination, the unintended transfer of contaminants from one process or tool to another, poses a serious risk, contributing to 8% of defects. Each of these process-related factors can reduce yield and reliability if left unchecked. That's why root cause analysis is so essential. Understanding the origin of these variations allows for targeted improvement strategies, ultimately reducing waste and boosting production efficiency. Inspection methods overview. Defect detection in semiconductor manufacturing relies on advanced inspection technologies, each tailored for specific types of analysis. Optical inspection uses light-based detection methods. Its capabilities include identifying surface defects, verifying patterns, measuring dimensions, and spotting color variations. Optical tools offer fast inspection speeds with a resolution around 200 nanometers, making them ideal for high-throughput surface inspections during patterning and overlay steps. E-beam, or electron beam inspection, uses electron scanning to achieve ultra-high resolution, down to about 1 nanometer. It is slower but more precise. E-beam is especially effective for detecting critical dimensions, voltage contrast, and buried defects that cannot be seen optically. It excels in critical review and analysis phases, where detail matters more than speed. X-ray inspection provides penetrating imaging, useful for non-destructive analysis of internal features. It detects voids, analyzes material composition, and evaluates package integrity. With resolution around 100 nanometers and moderate speed, X-ray is well suited for 3D analysis, void detection, and inspecting internal structures. Together, these methods form a comprehensive toolkit for identifying defects across different process stages and material layers. Inspection Methods Overview, Part 2. Additional advanced inspection methods provide greater flexibility in semiconductor defect detection. Laser scanning offers high-speed surface topology measurement with a resolution of approximately 50 nanometers. It is particularly useful for capturing surface contours rapidly. Atomic force microscopy, or AFM, provides ultra-high resolution, down to 0.1 nanometers, by mapping surface forces, making it ideal for nanoscale surface analysis. Infrared inspection focuses on thermal and subsurface imaging, with a resolution near 1 micron. It's valuable for detecting deeper or thermal-related anomalies. Confocal inspection enables 3D optical sectioning with about 150 nanometer resolution, offering depth-resolved imaging of sample structures. The technology comparison matrix summarizes key differences. Optical tools offer medium resolution, high speed, low cost, surface-level penetration, and full automation. E-beam provides ultra-resolution, but is slower and more costly, with limited penetration and medium automation. X-ray offers good resolution, medium speed and cost, full penetration, and high automation. A multimodal approach, combining these technologies, ensures broad coverage, greater accuracy, and cross-validation. This strategy enhances defect detection at various depths and process stages, enabling more robust process control and yield improvement. Advanced inspection technologies. AI-powered inspection technologies are transforming semiconductor manufacturing with unprecedented precision and efficiency. In the realm of AI and machine learning, intelligent pattern recognition is achieved through 4 key pillars. Deep learning leverages convolutional neural networks for feature extraction and pattern classification, enabling systems to recognize even the most subtle defects. Auto-classification handles real-time defect sorting and severity assessments while providing insights into root cause correlations. Predictive analytics uses trend analysis and failure prediction to optimize processes and reduce downtime. Adaptive learning ensures continuous model refinement, driving ongoing improvements and recognizing new defect types as they emerge. These capabilities deliver 99.8% accuracy, operate 10 times faster than traditional methods, and are available 24/7. On the frontier of emerging technologies, quantum sensors promise atomic-level defect identification beyond 2025. Digital twins are already modeling processes virtually for optimization. Hyperspectral imaging, emerging in 2024, analyzes chemical composition via spectral signatures. Edge AI processing is active today, enabling instant, on-tool defect detection and response. Advanced image analysis with computer vision. Computer vision is revolutionizing image-based inspection through advanced image analysis techniques. At the forefront is multispectral imaging, a newly introduced capability that captures information across different wavelengths of light, revealing hidden defects invisible to the human eye. This enables enhanced defect characterization and better process insights. 3D reconstruction, an active technology, converts 2D images into high-resolution 3D models, allowing for a complete understanding of surface topography and structural variations. This helps in identifying voids, cracks, and other anomalies that traditional imaging might miss. Real-time processing, a core function, ensures immediate analysis of image data, supporting quick decision-making and minimizing process delays. The integration of these technologies brings significant benefits. Inspection is now 50 times faster compared to traditional approaches. Costs are reduced by 30%, thanks to automation and reduced manual labor. Accuracy reaches 99.9% for defect detection, and 95% of operations are now automated, greatly minimizing human intervention. Technology Evolution Roadmap. The evolution of inspection technologies in the semiconductor industry reflects a rapid and ongoing shift toward intelligent, predictive quality control. From 2020 to 2022, the industry leveraged basic AI and machine learning tools for simple pattern recognition and automated sorting. These foundational steps introduced speed and consistency, but were still limited in adaptability. By 2023 to 2024, the focus advanced to deep learning, enabling real-time processing and the fusion of data from multiple sources, called multimodal fusion. This stage allowed systems to interpret complex patterns and respond faster to inspection demands. Looking ahead to 2025 and 2026, quantum sensors, edge AI, and predictive analytics are set to dominate. These will drive atomic-level accuracy and local, on-tool processing. Post-2027, we anticipate the rise of fully autonomous systems that self-optimize and aim for zero-defect manufacturing. The future of inspection is indeed intelligent, transforming inspection from a reactive task to a proactive and predictive quality control strategy.